Okay, so yeah, let's start the second lecture. So this is lecture 2. Yeah, so this is representation theory of finite dimensional representation. So finite dimensional reps of Lorentz group. So just let me do a quick recap of what we did in the last lecture. So I introduced Minkowski space with a particular convention. So this was R4 with a quadratic form that was defined like this. So I briefly say the signs was plus, minus, minus, minus. This was Minkowski space. And isometries of this quadratic space, we defined define Lorentz group to be that. So Lorentz group by definition. So now let's fix the notation. So the notation is O1, 3. So 1, 3, and O is orthogonal for isometries of this quadratic form. Okay, so this is we saw that it's a 6-dimensional real Lie group. I also mentioned that it has 4 connected components. So it's good to have this kind of picture in mind, mental picture in mind, the connected components of it. So this is this one, the connected component identity. This is the component that has the parity that changes the orientation of a space minus, minus, minus 1. And this is the component that contains time reversal. And on space is orientation preserving, and so. And this one is the component that contains PT. Now, in reality, of course, I did not show that these are connected. So this means that we have, but they are separately, certainly disconnected. So it has at least 4 connected components. So we have to go a little deeper into the structure of Lorentz group in order to understand what's the topology of this part. If you understand this part, you can understand this completely because this is obtained by multiplying by P. And so this is just by translation, you can get topology of everything. So we just have to understand this. And this component was SO13 plus. It preserves the space orientation and it preserves the time orientation. So this, by the way, this kind of decomposition of the Lorentz group has to do with a certain structure inside the Minkowski space itself, which is the following. So if you look at Minkowski space, we can designate the time axis, the positive direction by x0 here, and the space, so it has like the other 3 coordinates x1, x2, x3, or these 3. And here is the light cone. So so this is light cone. So vectors that are inside the time forward part of the light cone, they are called time-like vectors. So these are time-like vectors. So the time-like vectors then has 2 basically components. One is for positive x0, the other one is for negative x0. So there are these 2 connected components here, and there is a third one, which is the rest. So the rest is called space-like vectors. Other vectors are here, space-like vectors. So yeah, and then if you look at a hyperboloid here, say norm of x0 squared, which is x0 squared minus x1 squared minus x2 squared minus x3 squared equal to 1, or in general, if you put it equal to n positive, so you cut down, and if you say x0, for example, is positive, then you're looking at half of this hyperboloid of two sheets. So one sheet is upstairs, and the other sheet is downstairs, which I don't look at for now. So this is like square root of m here, of course. Yes, this is the square root m. So these hyperboloids are important. They are called mass hyperboloids. So when we look at the unitary irreducible representations of the Lorentz group later on, hopefully, we'll see that they can be obtained by looking at these hyperboloids, L2 spaces of these hyperboloids. Some of these representations are, and the mass naturally appears in that, mass of the particles naturally appears in that family of irreducible representation. But for now, we are not looking at those issues. We just want to look at the Lorentz group itself and its finite dimensional representations rather than infinite dimensional ones. All right, so now one important thing to understand this sort of connected components is, and in general actually to understand, is to have another representation of the Minkowski space in terms of spinors, and spin groups. So I'm going to represent it now. So maybe I just write here. So okay, so now let M be. So this is like a space of Hermitian 2 by 2 matrices. Do I have a special notation for that? Yeah, so this is the set of all H belonging to M2C such that H is equal to H star. So Hermitian 2 by 2 matrices. Okay. So this is, of course, a real 4-dimensional vector space. That's clear. We also in random matrix theory we have seen these things. So dimension of M over R is equal to 4. Now we can actually write a explicit isomorphism, linear isomorphism, real linear isomorphism between this and R4. So let's write it. So R4 to this M. So we send a quadruple x0, x1, x2, x3 to, let's see, to x0 plus x3. Raise this. And then we have got x0 minus ix, oh sorry, x1 minus ix2, x1 plus ix2, and x0 minus x3. Okay. So obviously this is a linear isomorphism. The linear iso. Now, something very interesting happens with this representation of R4, namely this quadratic form, the Minkowski form here, has a very convenient representation. It's determined. So there's a very easy lemma, is that if you call this norm, so let's call this this map, I don't know, maybe sending x to m of x. But what happens is that the determinant of, well, this is like m of x, right? The determinant of m of x is equal to norm of x squared. Obviously, if you compute the determinant, you see that this is true. So if we put this determinant norm on these Hermitian 2x2 matrices, we are going to get a copy of Minkowski space. So, so what happens then is that M and determinant actually is isometrically isomorphic, not just linearly, but isometrically isomorphic to R4 and is Minkowski metric. So this is an isometry. In other words, everything you want to do with R4 and Minkowski metric, you can do with M and this determinant. And we'll see that actually this is a very, very deep fact. It has many, many implications. And we'll see some of it today. So, any questions, by the way?
So the number of connected components being 4, if you go into higher dimensional or less, or let's say like 2-dimensional Minkowski case, we just have one space, spatial dimension, and one time, you still get 4 connected components because you still have the same.
So, yeah, I believe you still get 4. Yes.
Okay, because they're based around those operators, right? Existing, and they exist all the time, I think, right?
What's that?
And it's because those is the rough idea. Oh yeah, okay, yeah. Sorry, that's it.
I missed the question. I'm sorry.
No, it's I was just wondering if because the operators always exist and the connecting components are always formed around them in the same way.
Yeah, you can do the same analysis actually, as long as you have two, you have plus and minus. It doesn't matter in how many numbers plus and minus appears. For example, in 6-dimensional space, you might pick 3 positive, 3 negative.
Ah, okay.
They all have 4 connected components.
Ah, okay. Interesting.
Yeah, exactly. In all dimensions. Of course, if you have only plus or minus, the connected components reduces to 2. That's like orthogonal. That's true, but we will see this business of connected components very clearly now, very soon. Okay. Any other questions? You're welcome. All right. Now, relation to Pauli spin matrices. Now you can see that I can write this as linear combination of Pauli spin matrices. Let's do that because that's kind of important and deep, actually. So you see this vector, I mean this matrix. You can write it as well. Let me just write it like this: as x mu sigma mu. I mean, I really want, I mean, sigma x. Oh, no. Actually, it's good. It's up. Oh, yeah, this is bad. I just screwed up my indices up and down. 2 and 3. That's better. So this is x mu, sigma mu equal to 0 to 3. Okay, so now in this, sigma 1, sigma 2, sigma 3 are Pauli spin matrices. I mean, for example, sigma 3 is 1, 0, 0, and minus 1. You can easily remember this one. And sigma 1 is, I have to look at my notes. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0 minus I, 0. Sometimes they are also denoted by sigma z. And this one is sigma x. And this one is sigma y. All of them are very useful notation. And sigma 0 is just identity. So this we can call it a Pauli vector. So that's where a 4 vector is turned into a matrix, Hermitian matrix like that using Pauli matrices. This is a very, very important presentation of Hermitian 2x2 matrices. All right. So what we can do with this now? Now we're going to use this and find a copy of Lorentz group actually acting on this Hermitian 2x2 matrices in a very interesting way. So let me introduce a group now, which you know, of course. This is the SL2C. So let us recall SL2C. Well, I mean, this is the set of all complex 2x2 matrices whose determinant is 1. Right? This is SL2C. Now, this SL2C, of course, is a complex Lie group of complex dimension 3. But you can also think of it as a real Lie group also, which has come in a real dimension 6. So, and when you see it as a real Lie group, obviously it's going to be 6-dimensional thing. So this dimension is the same as dimension of the Lorentz group. And you might guess that there might be a relation. In fact, there is a relation. So we're going now to define a map from SL2C to...
You're just out of reach of the camera now.
Oh, yeah, that's too bad. Yes, yes. Thank you. Yeah, so I just continue here. So we're going to define a map now from SL2C to isometries of this M in the following way. Let's see. So let's define a map. It's usually called K from SL2C to GL M. So it sends a matrix, SL2C matrix A to K of A, where K of A acts like this. K of A, if you give me a Hermitian 2x2 matrix, it's going to be A, H, A star. Right? So first of all, we have to note that this goes in the right place, namely, this is really, again, Hermitian matrix. If H is Hermitian, this is by design, is a Hermitian matrix. And it's 1-to-1 onto, that's not a problem. It also preserves the norm, because the norm is given by what we saw, the norm is given by the determinant. And this preserves the norm, because if you take the determinant of this guy, determinant of A over H is just determinant of A, H, A star. Well, this is that A, that H, that A star, but this is 1. So this is also 1. So it doesn't change the okay, so then what we can say? We can say that it actually goes into Lorentz group, because the isometries, isometry matrix is a copy of the Lorentz group here. So basically, we have defined now the map from SL to C. Now it goes into Lorentz group, but then we have to see what part of the Lorentz group it goes to. Well, we have to know some facts about SL2C, which are actually not difficult, using very basic linear algebra to establish. Namely, SL2C is connected. Okay, so because it's connected, then it sends it into the connected component of the identity. By the way, this K is a homomorphism, obviously. K is a homomorphism, right? I mean, okay, so how do we show that it's a homomorphism? So if I K of B, A, H, I guess it's a homomorphism. Sorry? It's a homomorphism. Yeah. Right? So this is okay. Right. So it's a homomorphism. And so it sends this connected group into connected component of the identity. So it sends it into SO13. Now we have to also check that it sends into the part that has the things positive. So it really goes into SO13 plus. Now, this SL2C also is simply connected. I may give a proof of this today, or I can maybe show you how to prove it after the talk. But we just accept it now. It's simply connected. So it's pi1 is. So now, what's the kernel of K? Well, I mean, the kernel of K is the set of all SL2C matrices that A star is equal to H for all H. And you can easily convince yourself that this consists of plus minus 1. So what happens now is that this K is a 2-to-1 homomorphism. So A is 2-to-1 map. And if we accept that this is simply connected, coupled with the following fact, you can, of course, because it's a 2-to-1 map, you know that in the neighborhood of identity, this is a diffeomorphism because it's going to be 2-to-1. So it's not going to do too many bad things in the neighborhood of identity. So basically, then if we have a map from this connected Lie group, which is a local diffeomorphism, the image is going to be connected. The image, and I don't know, I guess from this basically follows that the map is going to be onto. It's not so bad. Because the connected component of the identity is generated in any topological group by an open neighborhood of the identity. So because we can write everything as a products of elements in the neighborhood of the identity, so it's going to be the image is going to be everything. And this is just a diffeomorphism in the neighborhood of that. So there is something to think a little bit, but it's not too bad to convince ourselves that actually this is surjective, and in fact this is a twofold covering of this. So A is a twofold covering. Okay, so I mean, this is pretty good because it shows that yeah, because this guy is simply connected, you're accepting it. it's a universal cover of this guy. So it follows that the fundamental group of SO1 3 plus is just Z2. So from here follows that phi 1 of SO1 3 plus is equal to Z2. Is a cyclic group of order 2. We will see this in a different way soon, actually. Okay. Any comments or questions right now? Okay. Now I want to draw your attention to something very, very strange about this map. I mean, this map is really amazing if you think about it. So let me tell you why this map is so incredible and it's unbelievable that this map exists. So let me tell you why. You see, if you look at Riemann sphere, CP1, so this is a complex manifold of complex dimension 1. It's the simplest Riemann surface. So as with any Riemann surface, it has a group of biholomorphic automorphisms. So if you look at automorphisms of CP1, so by the way, what are automorphisms of CP1? I mean, automorphisms basically means that, well, they are holomorphic and 1, 1 onto. So basically, in this case, they are 1, 1 onto. They are orientation preserving because they are holomorphic, and they have to preserve the angle. They are conformal. So they are orientation preserving conformal maps. That's it. And we know what this group is. This group is just something that in complex analysis courses, in the first course, they tell you what the group is. Right? You remember what this group is? I think it's SL2C. It's SL2C, is Moebius transformations, SL2C, except we have to divide by center, plus minus 1.
Right. Yeah.
So this is really PSL2C. So this is the group of Moebius transformations Z into AZ plus B over CZ plus D, which we just write it as the matrix ABCD. And we have to divide by this plus minus 1 because, well, I mean, if you multiply by plus minus 1, it's going to be the same action on, I mean, the ratio is going to be the same. So it's okay. So this is fine. Now, what this shows, what this observation shows, it shows that the Lorentz transformations of this four-dimensional space, Minkowski space, which we have no way of getting into or understanding it, to live in four-dimensional space. We'll never, ever be able to live in a four-dimensional space. This group, I mean, so let me write it. I mean, here, PSL2C is really isomorphic. I mean, this map shows that if you divide by kernel, you're going to get isomorphic to the proper Lorentz group, right? So it means that proper Lorentz group is the group of conformal orientation preserving transformations of the sphere. So you imagine, I mean, it's not easy to imagine these conformal transformations of the sphere either. I mean, but still one feels that, okay, I mean, you can draw and you can see how points move. And the way that these points move here apparently has something to do with this four-dimensional thing. So I think the first person who noticed this was Dirac, possibly some mathematicians also independently. And then Penrose made it into a huge program. He really utilized this and turn it into something called twistor program. So it's a big thing in Penrose's thinking about relativity theory. But it starts from here. And actually, I was looking at Wikipedia. I mean, he says that this is called the celestial sphere. I mean, you can also identify this with movements of things in the sky. But okay, so I did not really read carefully, but maybe at one stage I will read that. But I mean, but this is a very non-trivial thing. All right. Any questions?
Will we learn about what the other components look like?
Yeah. So now what we have seen is that the component of the identity, connected component of the identity, is really like PSL2C, Moebius transformations, but the other ones are exactly similar, except that you have to multiply this by P, for example. You translate it, right? By one element, you get into P, this component. And then you translate this by another element, which is T, you get into this component. I mean, they're exactly the same. I mean, except that the other, and then there is PT. Okay.
So in terms of maps on the Riemann sphere, I guess PET and PT are not going to be nice automorphisms.
They are not there. Because
there's no way to imagine them?
Because these guys are orientation preserving, and these guys are not in this SO13 plus component.
Yeah, but is it like, is P maybe like, I don't think it is, but it could be like reflection in the equation.
Complex conjugation, maybe.
Yeah.
Yeah, I cannot say exactly, but it seems to be maybe it's possible.
Yeah.
It might be possible. But then what about T? I mean, and PT? I mean, this is we have access to this part most conveniently, it seems, but the other parts, it seems we don't. And yeah, so I mean, so the fact that this SO13 plus is not simply connected, it means that its representation theory is going to be complicated. So let me make a remark about this, and then we will start building a little bit towards the representation theory. Any other questions or comments? Okay. So now let's make the following remark. So this is of course, because this map is a universal covering map. It means that the Lie algebra of this guy, I mean, so we have this map K, right? From SL to C to SO13 plus, right? So this is a universal covering map of the thing. So it means that if you look at differential of this map from Lie algebra of SL to C to Lie algebra of SO13 plus, well, I mean, obviously this map is going to be a linear isomorphism, right? Is a linear isomorphism of real Lie algebras. Okay, so now well, I mean, but then we know what this Lie algebra here is, but V of SLC as a real Lie algebra, it is isomorphic to SL to C. So what is that? That's the set of all A belonging to M2 whose trace is 0. Okay. Trace of A is equal to 0. Okay, so this is a real Lie algebra. So what we're going to do now, we are going to approach the representation theory of the Lorentz group, first of all, first through the representation theory of its Lie algebra. And its Lie algebra is isomorphic to Lie algebra, so we have to understand the representation theory of this Lie algebra. So once you understand this, then we have understood the representation theory of the Lie algebra of the thing. And then what happens is that half of them are going to give us representations actually of SO13, and the other half, they have spin half integer, and they are not going to be representations of this one. They are really genuinely representations of this one, because this is simply connected. Because this guy is simply connected, there is a 1-1 correspondence between representations of this and representation of its Lie algebra. Complex representation, for example. Yeah. But this is not the case for SO, because it has some topology, so not everything lifts. So this is the complication that's going to arise. Now, before we move to identify this, to decompose this Lie algebra, let me give an analog of this K map for the unitary group, SU2. So, and then I will finish there. So let's look at the group O3. The set of all A belonging to M3 of R, such that A transpose is equal to A, right? So this is the 3x3 orthogonal group. Okay, so now to again, this has two connected components. O3 is equal to SO3 union the other part, which is the other component, which is orientation reversing part. And so what we want to understand, we want to understand this SO3. So now what we are going to do, we are going to now define a map from R3 to, so this one, we can, I don't know, maybe we can just call it H. The space H is the set of all A belonging to M2 of C. Hermitian 2x2 matrices that have, I believe, trace 0. So let me just check. I don't have it here somehow, but that's okay. So let's look at this space such that A is equal to A star, and the trace of A is equal to 0. So these are traceless Hermitian matrices. right? So, I mean, obviously, this is also three-dimensional space. So dimensional H over R is 3, and the map is defined in the following way. If you just send x1, sorry, x1, x2, x3, this time exactly in terms of all the spin matrices, x mu, sigma mu. So this is going to be equal to x3, negative x3, and then from what we had, x1 plus minus ix2, sorry. And here is x1 plus ix2. All right, so now in this case, we'll see that actually what happens is that the Euclidean metric in this case, so let's call this, I don't know how to call this map. Maybe we call it alpha. Alpha of x, so negative determinant of alpha of x is equal to the Euclidean norm of x squared. Yeah? You can see that, right? So because this is going to be negative x3 squared and the other one. All right, so then if a transformation now preserves negative Euclidean norm, it's going to preserve Euclidean norm itself as well. So what is the map now? So using this, we can define a map now from, now we can define a map from basically now SU2, so let's define that SU2. This is A belonging to M2 of C. Or did I? Oh, this is bad. No, then that's okay. That's okay. M2 of C such that A star is equal to 1, which is of course going to be equal to A star A. And let's not forget, determinant of A is 1. Let's not forget this. Because being in U2 means that the determinant has absolute value 1, but this one has determinant you want to fix. Okay, now let us define a map. This is the famous SU2 group to SO3. The map is like this, and again, let's call it K. I just use again the same notation as K. So K of some unitary matrix U acting on some Hermitian traceless matrix H going to be equal to U H star. Yeah. So, and you can, again, similar to the case that we had before, you can check that this is actually universal covering map, because you know that this group is simply connected and da da da. So this is actually the universal covering map of SO3. So K is universal covering map. SO3. So now what happens in this case? Okay, well, I mean, this is a three-dimensional Lie group. And oh, the map is 2 to 1, by the way, again, similarly. So kernel of K. So the map is 2 to 1, and this we can convince ourselves that it's actually simply connected. In fact, SU2 is isomorphic to S3. And we can write an explicit isomorphism, for example, using quaternions, which are Clifford algebra elements. We can do that. So once we have that, we do that, then we can convince ourselves that this guy is simply connected, because S3 is simply connected, and this map is the universal problem. So again, the upshot here is that the Lie algebra of this guy is isomorphic to the algebra of SU2 as real Lie algebra. So this is important. I need this isomorphism also soon. So not today, but we'll use it. So Lie of SU2, which we denote by SU2. These are the set of all skew Hermitian matrices of trace 0. Right? This is the set of all A belonging to C, such that A plus A star equal to 0, and trace of A is equal to 0. Traceless skew Hermitian matrices, and this is isomorphic to Lie algebra of SO3, which of course we usually denote by S. And if we complexify this, because we are interested in complex representation, so we can complexify this, and here something very interesting appears. You'll see that if you complexify as a complex Lie algebra, this is same as the Lie algebra of SL2C as a complex Lie group. So there is a little bit of kind of confusing isomorphism going on here. But eventually what we're going to show next lecture, hopefully, is that we can decompose this 6-dimensional Lie algebra of the 6-dimensional complexified Lie algebra of 6-dimensional Lorentz group as direct sums of 2 Lie subalgebras, complex Lie subalgebras, that are Lie algebras of SU2 complexified. And once we have that, we can start representation theory, reading representation theory of Lorentz group in terms of SU2. And we'll see that that isomorphism actually, it just comes from something that you learn in special relativity, namely, there are these rotations in the Lorentz group, which are orthogonal things, because orthogonal is part of the game. And there are also these boosts, the hyperbolic rotations. So there are 3 boosts and 3 rotations, and they define 6 generators of the Lie algebra with some ingenious multiplication by I, everything works. Without I, nothing works. So the isomorphism is not true over the real numbers, it's true over the complex numbers. And that's the first step towards understanding finite dimensional representations of Lie algebra of the Lorentz group, complexified, complex representation. And okay, so I think we are good for now. So any questions or comments? Okay. Everything okay, Nathan?
Yep.
Cool. So I just stop the thing now. So, all right. So then till next time.
Mm-hmm. So tomorrow we're doing, Luke's going to present, right? At the same time?
No, Luke is going to talk today. Is that
talk
okay?
today?
Yeah.
Yeah.